Okay, I'm back. So I'm going to attempt to do my best to explain the properties, or some of the properties that make sense, physical sense, and through means of physical and physics capabilities, uh, the properties of dark matter and what goes on there. Okay, so I'm going to need a board. So I'm going to be starting by talking about matter, okay? And what I have to pick a point to start, and I'm not going to be talking about the creation of matter yet. I will get to that, okay? I'm going to start, essentially, if we look at this in a timeline, I'm basically starting in the middle, and I will get to how matter is created. And that's actually the beginning, but I got to start in the middle to explain it. Okay, so matter, okay, in this universe and wherever it is, matter, okay. There is a bubble, okay, surrounding matter. Basically, the matter has a given amount of space, and it pushes the dark matter away to a specific amount. Depending on the chemical composition of what the matter is, will depend on how far it pushes it. So I'm not going to get into which chemical does what. I just simply don't have enough time to explain that. And I haven't even looked into it yet, to be honest with you, but I'm sure that with different elements, the push on dark matter is different, okay? More or less, more push, less push. So, matter. Now, this is what we don't see, this ring. That is the matter pushing away on the dark matter, okay? That is essentially its own gravity bubble, okay? Now I wish I could cite where I got my information from, and I really apologize for that. But I have heard that no two objects can ever meet. Well, that isn't entirely true, okay? Because when you get into fusion, they do actually meet, okay? Now on a subatomic scale, they may not, but they connect. I'll get into that later as well. For all intents and purposes, I'm going to start as small as I can and build my way up, okay? Eventually getting into the size of a star, okay? Now, obviously, I don't have a lifetime to explain everything in detail, so I'm just going to highlight the bullet points. Okay, this is all about dark matter, the properties of dark matter. So, let me just write that. Sorry, I don't really think ahead when I start making these videos. I just understand the information and I gotta put it out there. Properties of dark matter. All right. So, the mass inside exerts a force and it actually pushes the dark matter out. So it's actually stretching the dark matter. It's actually stretching it, okay? Just one piece of matter stretching the dark matter. Now that creates, because it's being pushed away, the dark matter actually wants to collapse in on the matter, okay? So it's got a tension. Um, and actually, since it's got a tension like that, we can call that an attraction, okay? It wants to go in on itself, okay? Just the the bubble, okay? Now this is what we can't see. The bubble is what we cannot see out there, okay? So one piece of matter pushes the dark matter away. The dark matter is being pushed away and held away by the matter. That effect of it, the dark matter itself wanting to collapse, puts an attractive force on that particular piece of matter. Okay? Now, let's add another piece of matter. So, there's another piece of matter. There's the displacement. I'm going to call it dark matter displacement. Okay? Which is also has an attractive force. It wants to go in. Now, when there are two, okay, and there is movement, there's always movement in space. When these things come close to each other, they are actually attracted to each other, and the vibration, the tension on the dark matter bubble actually acts as a calling card for, and when another piece of mass gets close to it, it's easier for them to get intertangled. Okay, so now when you get two pieces of mass intertangled, so you'll have two, and for now, I'm going to say that the dark matter itself doesn't break. In fact, I'm pretty sure that it never breaks. Okay, it can only be stretched. It can be stretched quite a bit. Okay, so now when you have two pieces of matter, I want you to kind of note the size of this circle. Okay, I'm going to call that the dark matter displacement size or whatever. Add the size of both of these together. Now, if the dark matter can't be broken and only stretched, okay, so I have two bubbles. The mass wants to be close to each other. So it actually squeezes the dark matter out, away from the center of the mass. That's not a very good line. It should be more like that. So the dark matter is squeezed. Now, okay, so it's squeezed. It still has all the effects of the individual pieces of matter. Okay, it still wants to collapse in on itself. All right. Now, when you get two small pieces of matter, no matter how small they are, okay, the size of the displacement, okay, you see, it's a little bit bigger here, and that's just because it's being stretched. The actual bubble itself is, if you force it on one side, it's gonna release out the other way. So it's getting forced where these two pieces of matter are closest. It's being forced together. And it actually squeezes it similar to squeezing a balloon If you had like one of them hot dog shaped balloons and you squeeze it in your hand, the air goes up and the air goes out, you know, it's similar to that. And I hope this is a word, circumferentially. Circumferentially. Squeezes out circumferentially. I'm not even sure if that's a word. In a circle. Circle is the two-dimensional description. Spherically might be it. It squeezes out spherically away from where the matter is. Okay? So actually, it gains in size. Okay? It gains in size. Now the exterior does become a bit weaker. Okay, out here on these edges, it will become a bit weaker, but it is not broken. It does expand a little bit, adding more volume inside, simply because of the pressure of the two pieces of matter coming together. It's like these two bubbles come together, and you can just picture it. They come together, and it squeezes the dark matter out of the way. Okay? So, what this describes, and now obviously when we get more matter, it squeezes the dark matter even more, and the displacement spheres get substantially bigger. The more matter you get in here, it gets this displacement will just get much bigger, because each piece of matter has a given amount of displacement. And then I'm sure it has to do with chemical composition. Again, I'm not getting into that right now, though. Each piece of matter has its own set amount of displacement. So, you know, you get 4 items, you're going to have 4 bubbles, but then you have to calculate the squeeze of the 4 pieces of matter in close proximity. How much of the displacement is being squeezed away from the center? So, as you can see, as you add more and more matter, the squeeze can get more intense and more tighter and more packed fit. But with every piece of matter that you add, the displacement has to have its set amount of area. Okay? It's got to have its set amount of area. So it is stretched. You start getting 40 or 50 or 60 or 70 pieces of matter. They all have this much. But because they want to be close to each other, it forces this bubble, you know, it's got to have that room, but it forces it out that way, spherically away. Or not cylindrically, spherically, better description. Whatever. Anyway, so the more and more matter we get, the more inflated the displacement, the dark matter displacement, has to become, so it can maintain its original size. It just gets stretched. Now here's the neat thing, okay? Here's the very neat thing. And now when we get into a massive amount of matter being pushed together, okay? And I'm going to say this, there are thresholds, and I'll go over what that means here in a little bit. So when you get mass amounts of matter that are doing this and basically inflating the dark matter, it's basically inflating it. Now, we can't look at inflation, that word inflating is not what's going on. It's being stretched. Inflating means you're adding, well, it could mean you're adding something into it, like blowing into a balloon. You're adding, it's not having any kind of device, any kind of material added into it. It's being squeezed to the point where it's got to stretch out. Okay? We are not putting material in, it's not getting bigger because we are putting, anything's getting put in. It's getting bigger because it's being squeezed at this end. Okay? Now, the fun thing about that is a vacuum, essentially, is a vacuum. When you start making something bigger, from the inside, you're creating a vacuum, or it's creating a vacuum. I don't know how many times I'm going to say that so I get it right, but so inside a vacuum. Now, I just watched something, I think by Jim Khalil or something, and he was talking about the Heisenberg uncertainty principle, which says, like, in a vacuum, you could have created like a positive and a negative that instantaneously show up and then instantaneously go away. Now, I can agree with that to a point. My guess is, and I don't want to talk about other people's methods at all, but the reason that they go away in that particular equation is because there is nothing of mass enough to hold it in its existence. Okay, and I'll try and explain what I mean here by that. So right here we have the expansion of the dark matter displacement. Okay, we have that expansion going on. I hate to say inflating. It's inflating from the inside without anything there. It's being stretched from the inside. So what happens now in that empty space that's being stretched? Okay, so that we're getting into a whole nother line of physics here. All right. So when you have a bubble, okay, and you're not adding material into it, but the bubble gets stretched, you know, it's squeezed at a point and gets stretched, okay, it's taking up more space. Its volume area is encompassing more space. So it actually, you know, the dark matter that's outside of this, we don't even have words for this stuff yet, is just pushed further away. But the displacement bubble, because it's being inflated from the inside, okay, what's happening? Now this is the real neat stuff here. What's happening on the inside of that? And here is a good term or a good idea on where matter comes from. It basically comes from nothing. Okay, so when you stretch, you have your original bubble. When you stretch it out, it becomes bigger. What's happening to that air inside? Okay, well, the air inside, let me draw another picture here. Okay, and just to describe it with lines, okay, just out from the center, you know, Just look at it like it's some kind of material that's being stretched from the inside. Well, when this gets bigger, okay, that means the material on the inside is getting stretched. Okay, what's on the inside? There's nothing on the inside, but actually there is. Okay, the dark matter displacement bubble is what encompasses the matter. Okay, now we don't know exactly what the material is, but there is something there. So when you inflate that dark matter displacement bubble, the material that's in there gets stretched. Okay, it gets stretched, which can, gosh, this is hard for me to describe. It creates a tension inside specific areas in that bubble. There is a tension created just by stretching out the space inside that bubble. Okay? So that tension I will get back to in a little bit. It's important to know that that is happening. Now I'm going to jump up here. Okay? Another way to look at this too is we got the tension going on there, so that's a different chapter, but still necessary. When we hit another threshold, okay, when we have lots of mass, okay, or lots of matter, the displacement will happen at a large amount. The stretching of the dark matter, the displacement, when I just talked about the inner material, it'll be stretched, and it'll have, if it's being stretched and it's got tension points, that means it's also got weak areas as well inside the bubble. Okay, so as this, if we look at it like it's a star with planets going around it, as the dark matter propagates itself away from the matter, okay, there'll be zones, and this is generally why we see kind of specific distances from the planets to the star's core. It's kind of set distances, and it's the same with I believe electrons, and I'm not sure, I'm not that kind of scientist. I'm not a scientist at all, as a matter of fact. But there's set of distances, okay, where the dark matter is kind of propagates away from the center. Now it's still there. I say propagates away. It's expanding away depending on the amount of mass. And if you don't add more mass, it's not going to keep growing. Or if you don't add matter, it's not going to keep growing. The more matter you put in, the more it grows. You stop adding matter, it stops growing. Okay? But now when you hit a point when there's a specific amount of matter, I believe what happens is a vortice will be created. We call that a weak or a strong area. It's a relax point for on the interior of, gosh, this is pretty mind-blowing stuff. It's a relaxed point on the interior of the total dark matter displacement. Okay, it's stretching out, and there's a relaxed zone. Okay, it kind of does one of these. Now I'm showing this here, But we know that, especially if we look at our solar system, you know, if this is Mercury, this dark matter displacement goes way out. Way out. We're talking Oort cloud out. Um, so the vortice is created. Now, inside this vortice, we know Mercury is traveling. Okay. Well, how did Mercury get there? You know, this and that. So going back to there's a popular theory right now, and that it's an accretion, and there was the dust, and the sun formed in the disk, and then all the planets got formed from the remainder of the dust, and that's totally possible. Another is that some dust could be collected to create the planet Mercury. Uh, some of it, I believe. Now, here's a pretty far out theory. Well, I was getting into what I said before about stretching the dark matter from the inside. Okay, how it can get tense or weak. Well, if you stretch it out from the inside, okay, that material inside can act like a rubber band, essentially, with too much tension. It springs back, okay, and if it breaks, it springs back, creating a vortice. That vortice. Now here I'm getting into saying it breaks. I'm figuring this out as I go. So that's another theory right there, is the expansion itself creates matter simply by stretching the material out inside that dark matter bubble. You know, this material, stretching it out to the point where the tension inside actually creates a zone where the energy is released, and that could be a zone away from the center of our sun at the distance of our planet's spacing. Okay, it's a relaxed zone. Or a tension release zone. Okay, it's where the stretching of all the dark matter that's there can reaccumulate itself. I wish I could do some imagery generated by a computer to show this, because physically in my head, I can see it making sense. Properties of dark matter. Okay, so basically, now the matter itself. Okay, now I'm going to get into the creation of matter itself, and here's where I'm like jumping off a darned cliff with anybody in the science community, probably. So matter itself, I'm going to say, matter itself is created by the stretching of the dark matter, the stretching of this original bubble, and what is happening with the area inside there. It's being stretched out. So now, depending on the contents of what type of matter you're dealing with. This is a stretch to say that elements pop into existence um, as a kind of a relaxed zone. If the material inside this dark matter bubble reaches its stretching point, okay, uh, maybe there's a vibration running through the material, and that vibration is a physical. It's actually a physical force. It's a real physical force. So if it's an actual physical force, what is it actually physically? Where is the force coming from? Well, the force is coming from the stretching. If you're pulling like a rubber band, the force is coming from the stretch. You stretch that rubber band out, and there's all kinds of tension there. So there's the physical force that's being stretched. In a relaxed zone could be the crystallization of the tension. The tension may reach specific pressures or specific tensions to the point where it crystallizes, and it's just not going away at that point. That tension's there, and it crystallizes. That tension itself actually crystallizes and becomes a piece of matter. Is that possible? Does that make sense? Where that tension itself, and if it's not crystallized, I mean, it is cold in space. So crystallizing could be where matter comes from. Because there's a physical force, we can't see it inside the dark matter. But if it's being stretched out, that means whatever is inside that area, whatever inside this original bubble, is getting stretched out that we can't see, but there is obviously it's going to be stretched out, which means there is a physical force inside there, which has a tension to it. And when that tension gets super hard or super tight, you'll have points where it'll harden. Crystallization, I guess, could be a word to use for that. So I'm basically saying that by habit of this stretching, the physical phenomena that goes on with stretching this, the tension inside actually creates matter. It creates matter. Now, the different elements and whatnot, I'm sure it's 100% specific to what type of matter you have in your original mass. Okay. Now, I said that, and that's I'm going to be called a crackpot for that, but I believe it's totally possible, and probably why there is way less matter in the universe than there is dark matter and dark energy and all that. And that would be a good estimation. But I haven't run any of the math. I'm just looking at my picture. I'm like, okay, yeah, that looks to be about in line with what we're seeing. Okay, so I want to go a little bit further now. And I'll be happy to work on, I'm going to work on this as much as I can. I do this in my spare time. but I'd be happy to discuss with people who are interested. Okay, so I want to talk about fusion now. So fusion is when we actually, let's put our dark matter bubble in there. Fusion is when we actually connect these together, okay? So what happens to each piece of matter's bubble, okay? When fusion happens, I am going to say that these bubbles become one, okay? So you'd have your two pieces of mass here. I'm going to draw them like this and just keep the line in the middle. But then we'll lose this. Okay? And that's where did you ever see those blow up bubbles when they come together? Yeah, they can actually, and then when they do come together, they'll have a thicker shield because there's more material there and whatnot. So that actually creates a stronger dark matter displacement bubble. The perimeter is stronger. Okay? And that happens with fusion. Now, obviously, fission would be the same thing in the opposite direction. Okay, so if we broke these two apart, it would be, so let me see, fusion would be a combining, fission would be a separating. So essentially we'd be slicing the perimeter strength in half. Okay, it would be almost like it'd almost be like there's two layers now. If these were still connected, okay, it would almost be like there's two layers. When we disconnect it, one layer goes back to where it was at. Okay, because now each piece of matter has its own displacement bubble again. So that's that's basically the dark matter collapses in fission. It's weird. It seems like it shouldn't do that, but in fission, the dark matter actually separates and collapses. Okay, back around its original particle. And on both accounts, if fission does one split, each particle will have its dark matter displacement bubble collapse back down in on itself. Whereas fusion, it actually is more like an explosion. So fusion actually doubles down on the bubble itself. Okay? And that's important to know about the doubling down. So you have double strength now with this dark matter displacement bubble. And double the strength means you'll have double the force of the dark matter wanting to collapse back in itself. Okay, you'll have double. The other one I drew, it was the arrows were further spread apart, which makes this more of an attractant. Okay, makes it easier for elements or pieces of matter to come in contact. Alright. So the reason I've been doing all this, trying to figure out this dark matter situation is, and I'm going to step off another cliff here, is I've been trying to find a way to beat the speed of light limit. It's like looking at a speed limit sign on a highway that no one can ever go faster than. I can't stand that limit. So I'm trying to find a way to move faster than light. And I'm like, well, okay. So I can't use light to do it. I have to use this mystery stuff. So I'm going to look at the dark matter displacement, okay? So if we have our, let's just go planet wide, okay? Or star wide, okay? So we have our sun. Oh, excuse me. Sorry about that. And then third rock. So the displacement of the sun, okay, is obviously huge. It's obviously huge. You know, and then the relaxed vortices create the ability for Mercury, Venus, and all other planets. The relaxed vortices made it possible for these planets to accumulate or crystallize, like I explained before. You know, this is something that another theory that I'm going to throw out there is that the planet could, if my theory is correct, actually be growing from the inside. Okay? Our Earth could be getting bigger from the inside. Okay? Yep, I did say that. I did definitely say that. And I believe that it's true. It could be true. Because, again, with saying the inflation and stretching and the crystallization of the tension inside the dark matter displacement bubble, the crystallization or that's crystallization, is that freezing? Whatever. It's a force of tension that happens on an invisible substance, but it's got to be there. There's something's got to be there. And matter is actually created from that. So our planets could be accumulating new matter from the inside. Just new matter from the inside with forces that we don't quite understand yet. We definitely can't see them. Definitely can't see them. So I'm going to get back to this with moving faster than light. Now this, I don't even know if this is a possibility, but I have to think outside the box to try and beat the light barrier. So we know that, and I grabbed this dark matter stuff because it might be an avenue. The sun, dark matter displacement, has far-reaching, we know, it's very far-reaching. You know, Jupiter's magnetosphere is very far-reaching. So, what I would like to do is be able to somehow access these actual dark matter tendons, where the dark matter is being stretched. You know, we don't have to go to the center of the sun or at all. We could probably do it because the Earth's got its own. You know, the Earth's got its own magnetosphere. Access those tendons. Okay, so the sun has actually got a vortice created for the Earth, and it's got one created for Venus and Mercury, and then on for the big planets. And you get into the deeper physics when you get further out. the same, but just a larger calculation. So, what was I saying? Okay, so we know, or I believe, that this is actually being held into place. Okay, the Earth is, and that's another thing. The Earth and these planets will never drop in to the sun. They'll never, unless the sun starts coming apart, the planets will never drop into it. They are locked in their distance away from the sun. Okay, they're locked in, and that has specifically to do with the dark matter displacement, the amount of displacement, okay, that is required. Now, we have 9 planets. There may be stars out there that have 30 planets, you know, or there may be stars that only have 1. But it'll be a direct relation to how much mass is in the star with how far away the planets are. It's all about the stretching of that dark matter and the vorticity that is created in the relaxation of the dark matter displacement. Okay, it's actually a relaxation point. You can look at the Earth going around the sun, and the entire cylinder is a vortice around the sun. Okay, and the Earth itself is the accumulation of either elements created inside of it or a collection of particles from around, which seems to be the popular belief. I'm kind of leaning towards inside. It's growing from the inside. That's a little stick my foot in my mouth theory with that, but it is totally possible. It's just forces that we cannot see or totally understand yet, but they're there. They're there. Okay, so what was I saying? Okay, so I'm still trying to break the speed of light barrier. All right. So my thing is with the, I'll erase all these lines here. I'll redraw my Earth. Okay, so there's Earth, and there's its magnetic poles. Okay, what I want to do is attempt to access the magnetic poles, which could actually be Earth's own dark matter displacement. Okay, because it is a ball of matter, and all that matter's got its own dark matter displacement bubble. So we actually do, and we kind of understand it as the Earth's magnetic field. But that magnetic field could actually be the dark matter, and probably actually is the dark matter being stretched out just like it is from around the sun. Okay? I want to attempt to access those tendrils. Okay? Now, we can see them. The northern lights. Okay? The beautiful northern lights that shine down. Those are actually the tendrils being lit up by ionized gases or whatever it may be. We're actually able to see those tendrils. And when you see them, it's like a bunch of little lines. Those are the tendrils that I'm talking about. Okay? Now, I don't know, and I hope that it would be true, because it would open a door to a whole brand new thing. If we could access these things, okay? Basically communicate through them. You know, can I grab one of these tendrils on the North Pole and push and pull on it and have that information transfer around to the adjoining tendril on the South Pole? You see what I'm saying? You know, we know that there's a return on all of them. That they always return. Finding which one could be pretty tricky, unless we build a device to be able to hone in on which one we're pulling up here, and then like some kind of oh, it's that one over there, a reader to read which one of these tendrils we're pulling on. And since it is, and now here's the thing, since it is connected, it's actually the dark matter displacement bubble. Since it is connected back in, it is physically, there is a physical connection that goes all the way out and back in. Safe to say that if we could grab one of those, and if it was like a rope, and if we could grab one of those, how long would it take for that shake or vibration to return back to the earth? And that is where I'm hoping that the speed of light barrier can be broken. I'm hoping. I don't know for sure. I would like to say that it's darn near instantaneous. You know, if we have one of these tendrils, we grab one of them, I'm hoping that that is like an immediate effect as far as it has to travel. You know, if it's, how big is the earth? 10 miles from side to side, right? The earth is 10 miles wide. So if this thing goes 100 miles, you know, obviously I'm full of it here, but if it's 1,000 or 100,000 miles or whatever, this tendril is 100,000 miles long, and I can shake it at the top or add some kind of wiggle to it to where I could measure it on the return. How long would that take? You know, is it instantaneous? Does it feel it right away? Would it feel it all the way through? Or, you know, if I'm grabbing it here, would the shake go out this way, or would it go through the planet and come around the other way? I think that depends on, you know, we might be getting into North and South Pole there with that. But that's a pretty strong, these tendrils are, even though we can't see them, say for the northern lights, they're very strong. I mean, they run through the entire core of the planet, the entire core of the sun. Now, they'll get tangled up inside there because there's so much matter inside these planets and suns. There is so much matter in there. The tendrils, of the dark matter displacement is what I'm going to call it. Those tendrils are just all over the place, wound up. That's could be a good reason why when we look at the sun as it is, you see these monster just arcs, and it's these tendrils that are just wound tight through. So it's very neat stuff. So now, like I said, my whole intention on trying to learn more about how this dark matter works was so I could try and break the speed of light barrier. Okay. Accessing these tendrils. Well, we all know we can't just go up and grab one. Okay. We have an idea of what they are. We can kind of see them, you know, but they're like basically air, you know, we can't grab them. So how would we access them? Okay, now I had mentioned in another video I did about maybe using sound. Okay, this is a big process. So this is a huge process. I mean, first of all, we'd have to locate these tendrils. Okay, now they're all over the planet, but the big ones are at the poles. Okay, it might be easier finding the big ones first, but we have to locate them. Okay, specifically. Okay, and the thing is they don't stay constant, they move. You know, just because the planet's solid doesn't mean that you got one tendril that's here all the time. Those things move inside and through the planet. They move around. They have to, because the mass inside the planet, the matter inside the planet's moving around all the time. So all that dark matter displacement is getting twisted around inside the planet, all kind of munched in with each other, but those tendrils don't break. So those things will move. I mean, they from the core of the planet to the top, they can move 50 miles in 3 seconds. You know, it's just there. It's just the way the core of the planet is moving around, that these tendrils will move. So that creates a pretty big mountain to climb. Number one, well, we already had a big mountain to climb. Number one, we got to find these tendrils. We got to locate them. Okay, we got to be able to see them. So there's a big challenge. Number two, they're moving great distances. They move like you could set up a base camp, find a tendril, and 3 seconds later, that thing's gone. So being able to watch a tendril move, okay, we're going to need specific equipment to watch the tendril move. You know, we can see it on when we're standing on the surface if we had a machine, and could kind of highlight the tendrils. We could see that they're moving all around. You know, they still project out away and return. So there's a thing is locking down on a location on one of these tendrils. Somehow getting locked to one, even being carried by one, would be ideal, because then we wouldn't have to worry about moving base camp every 2 seconds, or in a vehicle trying to drive these things down. You know, maybe a flight vehicle could keep us pretty close to one. You know, a drone or very acrobatic plane might keep us in close enough proximity, once we find one, to one specific tendril, which we then may be able to produce some kind of force on, whether it be sound. You know, I thought before in my other video, I thought sound, if we kind of shot sound at this thing, it would add a vibration to it. And we literally have to follow that tendril all the way wherever it goes, as far out in space it goes, back round to its return, to see if that information was transferred. So it's not an easy task. I'll keep thinking about it, trying to figure out a way that it might be possible to do it, which is going to be very difficult. But it'd be interesting to know how fast the information is transferred. I'm pretty sure if we could grab a hold of it, that information is definitely transferred all the way out through that tendril, all the way back to the return. I'm guaranteeing it's transferred. So my thing was then, if we could climb all these mountains that I just built in front of us, and grab and transfer that, how fast does that transfer happen? You know, how fast did that information do its run and return? Hopefully faster than light, because that's what I'm going for here, is hopefully faster than light. Then again, you know, as far as, you know, what's out there and whatnot. So these tendrils are all over the place. Okay, the sun's got them, we've got them, the planet's got them, even the moon's got them to some extent, you know. On a bigger scale, we are inside a galaxy that's filled with them. Okay, it's not just our solar, it's every star out there has got them. Every galactic center has got huge, huge ones, you know, so it's an invisible thing that we can't see, and we're kind of alone in our galaxy. But is there tendrils that are connected from galaxy to galaxy? Are there? That would be my whole point. You know, eventually maybe we'll find that. But more interestingly, is are there tendrils that are connected from our star to other stars? You know, finding them and accessing them. Uh, and again, if it's not faster than the speed of light, it doesn't really matter. But if they are faster than the speed of light, which would be great, if they were more of an instantaneous type of deal, that would be great. It would open the lines to possible communication to possible other civilizations. No need to travel if we could communicate, you know. And I believe right now that there are plenty of other civilizations out there, and the best way to communicate is not by showing up in person, it's by the transfer of information. Okay? And so I want to break the light barrier, speed limit, because that is just not fast. It's just not a good way to communicate. You know, if we receive a communication by light, that could be, you know, what, 1,000,000 years old or 10,000 years old. By the time we receive that information and understand that it's actually another civilization, their species could be dead and gone by the time we get around to figuring out to set a single signal back. That's why the speed of light is not good. We need to attempt to find a way to break that barrier, that speed limit barrier. And not for transferring matter, but being able to communicate, transfer communication. So that's an idea I had, and it led me, you know, like I know I have a belief that these tendrils are connected not only to our planet, but you know, our sun is connected to the galaxy. And how's it connected? And the dark matter displacement that I had just spoken about is a good engine to describe what's happening and how things are held together. You know, why the stars aren't flung off into it's because they're actually encased in a displacement bubble. Okay. Again, I said that I believe matter is formed inside the expanding displacement bubble, either via crystallization or some other means. Matter is actually formed inside the expanding displacement bubble. I'm done going about as far as I'm going to go today. I thank you for your time, and I'll move on to other things.